This presentation is delivered by the Stanford Center for Professional Development.
All right, so welcome back. What I want to do today is start a new chapter in our discussion on machine learning, and in particular I want to talk about a different type of learning problem called reinforcement learning. We'll talk about Markov decision processes, value functions, value iteration, and policy iteration. Both of these last two items are algorithms for solving reinforcement learning problems. As you can see, we're also taping in a different room today, so the background looks a bit different. So just to place this in context, the first of the four major topics we had in this class was supervised learning. And in supervised learning, we had a training set in which we were given sort of the quote right answer for every training example. And it was then just a job of the learning algorithm to replicate more of the right answers. And then we talked about learning theory, and then we talked about unsupervised learning. And in unsupervised learning, we had just a bunch of unlabeled data, just the X's. And it was the job of the learning algorithm to discover, quote, structure in the data. And so we had algorithms like factor analysis, k-means, mixture models filled with EM, PCA, ICA, and so on. Today I want to talk about a different class of learning algorithms that's sort of in between supervised and unsupervised. So it'll be a class of problems where there's sort of a little bit of supervision, but also much less supervision than what we saw in supervised learning. And this is a problem formalism called reinforcement learning. So let's switch to the slides. Let me show you, as a motivating example, here's an example of the sorts of things we do in reinforcement learning. So here's a picture of, some of this I talked about in lecture 1 as well, but here's a picture of an autonomous helicopter we have at Stanford. So how would you write a program to make a helicopter like this fly by itself? Let me show you a fun video. This is actually, I think, the same video that I showed in class in the first lecture. But here's a video taken, on the football field in Stanford of using a machine learning algorithm to fly the helicopter. So let's just play the video. And you zoom out the camera and see the trees in the sky. So in terms of autonomous helicopter flight, this is work done by some of my students and me. In terms of autonomous helicopter flight, this is one of the most difficult aerobatic maneuvers flown. And it's actually very hard to write a program to make a helicopter do this. And the way this was done was with what's called a reinforcement learning algorithm. So just to make this more concrete, right? The learning problem in helicopter flight is 10 times a second, say. Your sensors on the helicopter gives you a very accurate estimate of the position and orientation of the helicopter, so you know where the helicopter is pretty accurately at all points in time. And your job is to take as input the position and orientation, and to output a set of numbers that correspond to where to move the control sticks to control the helicopter, to make it fly the right side up, fly upside down, or execute whatever maneuver you want. And this is different from supervised learning in the sense because usually we actually don't know what the quote right control action is. And more specifically, if the helicopter in a certain position and orientation, it's actually very hard to say, when the helicopter is doing this, you should move the control sticks to exactly these positions. So it's very hard to apply a supervised learning algorithm to this problem because we can't come up with a training set of where the inputs are the position and the outputs are the right control actions. It's very hard to come up with a training set like that. Instead, in reinforcement learning, we'll give the learning algorithm a different type of feedback via something called a reward signal, which will tell the helicopter when it's doing well and when it's doing poorly. So what we'll end up doing is we'll come up with something called a reward signal, and I'll formalize this later, which will be a measure of how well the helicopter is doing. And then it'll be the job of the learning algorithm to take just this reward functions as input and try to fly well. Another good example of reinforcement learning is think about getting a program to play chess or Othello, a game of chess. At any stage in the game, we actually don't know what the quote optimal move is, and so it's very hard to pose playing chess as a supervised learning problem, because we can't say, you know, the X's are the board positions and the Y's are the optimal move, because we just don't know how to create any training examples with optimal moves for chess. But what we do know is if you have a computer playing games of chess, we know when it's won a game and when it's lost a game. And so what we'll do is we'll give it a reward signal. So give it a positive reward when it wins a game of chess, and give it a negative reward whenever it loses, and hopefully have it learn to win more and more games by itself over time. So one way I like to think about reinforcement learning is think about training a dog, right? Every time your dog does something good, you sort of tell it good dog, and every time it does something bad, you tell it bad dog, and over time, your dog learns to do more and more of the good things over time, right? So in the same way, when you're trying to fly a helicopter, every time the helicopter does something good, you say good helicopter, and every time it crashes, you say bad helicopter, and then sort of over time, it learns, you know, to do the right things more and more often. The reason, I mean, one of the reasons that reinforcement learning is much harder than supervised learning is because this is not a one-shot decision-making problem. So in supervised learning, if you have a classification, like predict whether someone has cancer or not, you make a prediction and then you're done, right? Your patient either has cancer or not, and you either right or wrong, they live or die, or whatever. You make a decision and then you're done. In reinforcement learning, you have to keep taking actions over time. Sometimes called the sequential decision making. So concretely, suppose your program loses a game of chess on move number 60. Then it's actually made 60 moves before it got this negative reward of, you know, losing a game of chess. And the thing that makes it hard for the algorithm to learn from this is sometimes called the credit assignment problem. And just to state that informally, what this is if a program loses a game of chess in move 60, you're actually not quite sure of all the moves you made, which ones were the right moves and which ones were the bad moves. And so maybe it's because you blundered on move number 23, and then everything else you did may have been perfect, but because you made a mistake on move 23 in your game of chess, you eventually end up losing on move 60. So just define very loosely, credit assignment problem is when you get a positive or negative reward to figure out what you actually did right or did wrong to cause the reward, so you can do more of the right things and less of the wrong things. And this is sort of one of the things that makes reinforcement learning hard. And in the same way, if the helicopter crashes, it may not. And in the same way, the helicopter crashes, it may be something you did many minutes ago that causes a helicopter crash. Right? And in fact, if you ever crash a car, right, hopefully none of you will ever be in a car accident. But if someone crashes a car, usually the thing they're doing right before they crash is step on the brakes to slow the car down before the impact. And you know, usually stepping on the brakes does not cause a crash. It probably makes a crash sort of hurt less. But so reinforcement learning algorithm may see this pattern that, you know, you step on the brakes, you crash, you step on the brakes, you crash. And that's how you figure out that it's not actually you're stepping on the brakes that caused the crash, but something you did long before that. Okay? So let me go ahead and define the and formalize the reinforcement learning problem a bit more. And as a preface, let me just say, RL algorithms are applied to a broad range of problems, but you know, because robotics videos are easy to show in a lecture, I have a lot of them. And throughout this lecture, I use a bunch of robotics examples, but later we'll talk about applications of these ideas to broader ranges of problems as well. But the basic problem we're facing is how to make sequential decision making, where you need to make many decisions and where your decisions may have long-term consequences. So let's formalize the reinforcement learning problem. Reinforcement learning problems model the world using something called the MDP, or the Markov decision process formalism. Oops. And let's see, an MDP is a 5-tuple. I have enough space. Well, comprising 5 things. Just write this here, I guess. So let me say which of these are. Actually, could you please raise the screen? I won't need the laptop anymore today. Just give me more chalkboard space. Actually, oh, maybe I need to. Oh, cool, great, thanks. So an MDP comprises a 5-tuple. The first of these elements, S, is a set of states. And so for the helicopter example, the set of states would be the set of possible positions and orientations of a helicopter. A is a set of actions. So again, for the helicopter example, this would be the set of all possible positions that we could put our control sticks into. PSA are state transition distributions. So for each state and each action, this is a probability distribution. So sum over S prime, PSA, S prime equals 1, and PSA, S prime, right, is greater than or 0. And state transition distributions or state transition probabilities work as follows. P subscript SA gives me the probability distribution over what state I would transition to next, or what state I'll wind up in if I take an action A in a state S. Okay, so this is probability distribution over states S prime that I might get to when I take an action A in a state S. Now I'll revisit this in a second. Gamma is a number called the discount factor. Don't worry about this yet. I'll say what this is in a second. And is usually a number strictly less than 1 and greater than or equal to 0. And R is our reward function. So the reward function maps from the real numbers, from the set of states to the real numbers, and it can be positive or negative. Okay, that's the set of real numbers. Okay. So just to make these elements concrete, let me give a specific example of an MDP. Rather than talking about something as complicated as helicopters, I'm going to use a much smaller MDP as the running example for the rest of today's lecture. And we'll look at much more complicated MDPs, in subsequent lectures. This is an example that I adapted from a textbook by Stuart Russell and Peter Norvig called Artificial Intelligence: A Modern Approach, 2nd edition. And this is a small MDP that models a robot navigation task in which, if you imagine you have a robot that lives sort of in a grid world where the shaded in cell is an obstacle, so that the robot can't go through this cell. And just number these. Right. And so let's see. I would really like the robot to get to this upper rightmost cell, let's say. So I'm going to associate that cell with a +1 reward, and I really like it to avoid that, that grid cell. So I'm going to associate that grid cell with a -1 reward. So let's actually iterate through the 5 elements of the MDP and so say what they are for this problem. So the robot can be in any of these 11 positions, and so I have an MDP with 11 states, and so this is a set capital S corresponding to the 11 places it could be in. And let's say my robot in this sort of highly simplified pedagogical example can try to move in each of the compass directions. So in this MDP, I would have 4 actions corresponding to moving in each of the north, south, east, and west compass directions. And let's see. Let's say that my robot's dynamics are noisy. So if you worked in robotics before, you know that if you command a robot to go north, because wheel slip or encoders aren't entirely accurate or whatever, there's a small chance that your robot will veer off slightly. So if you command a robot to move forward 1 meter, usually you'll move forward, somewhere between like 95 centimeters or to 105 centimeters. So in this highly simplified grid world, I'm going to model the stochastic dynamics of my robot as follows. I'm going to say that if you command the robot to go north, there's actually a 10% chance that it'll accidentally veer off to the left, and a 10% chance it'll veer off to the right, and only a 0.8 chance they'll manage to go the direction you commanded it. Okay, so this is sort of a crude model of wheel slipping on a mobile robot. And if the robot bounces off a wall, then it just stays where it is and nothing happens. So let's see. Concretely, we would write this down using the state transition probability. So for example, let's take the state, which I'm going to call the 3, 1 state, and let's say you command the robot to go north, right? To specify these noisy dynamics of the robot, you would write down state transition probabilities for the robot as follows. You say that if you're in the state 3, 1, and you take the action north, the chance of getting to 3, 2 is 0.8. If you're in the state 3, 1 and you take the action north, chance you get to 4, 1 is 0.1, and so on. Get to and so on. Okay. This last line is that if you're in the state 3, 1, and you take the action north, the chance of you getting to the state 3, 3 is 0, right? And this is your chance of transitioning in one time step to the state 3, 3 is equal to 0. So these are the state transition probabilities for my MDP. Let's see. The last two elements of my 5-tuple are gamma and the reward function. Let's not worry about gamma for now, but my reward function will be as follows. So I really want the robot to get to the 4. I hope this makes sense. I'm using 4, 3, to index into the states, right? Using the numbers I wrote at the sides of the grid. So my reward for getting to the 4, 3 state is +1, and my reward for getting to the 4, 2 state is -1. And as is common practice, let's see. As it's fairly common practice for navigation tasks, for all other states than the terminal states, I'm going to associate sort of a small negative reward. And you can think of this as a small negative reward that charges my robot for its battery consumption or its fuel consumption for wandering around. And so a small negative reward like this, that charges the robot for wandering around randomly, tends to cause the system to compute solutions that don't waste time and make its way to the goal as quickly as possible because it's charged for fuel consumption. Okay. So, well, there's actually let me just mention there's actually one other complication that I'm gonna sort of not worry about. In this specific example, I'm actually going to assume that when the robot gets to the +1 or the -1 reward, then the world ends, and so you get to the +1 and then that's it, and the world ends. There are no more rewards, positive or negative, after that, right? And so there are various ways to model that. One way to think about that is you might imagine that there's actually a 12th state. Sometimes called the zero cost absorbing state, so that whenever you get to the +1 or the -1, you then transition with probability 1 to this 12th state, and then you stay in this 12th state forever with no more rewards. But just mention that when you get to the +1 or -1, think of the problem as then finishing. The reason I do that is because it makes some of the numbers come out nicer and be easier to understand afterwards. But so this sort of state where you go in but sometimes you hear the term zero cost absorbing state to denote the state, so that when you enter that state, there are no more rewards. You always stay in that state forever. Okay. All right. So let me just say how an MDP works. MDP works as follows. At time 0, your robot starts off at some state S0, and depending on where you are, you get to choose an action A0. You decide, do I go north, south, east, or west? Depending on your choice, you get to some state S1, which is going to be randomly drawn from the state transition distribution indexed by state 0 and the action you just chose. And so this next state you get to will depend sort of in a probabilistic way on the previous state on the action you just took. After you get to the state S1, you get to choose a new action, A1, and then as a result of that, you get to some new state S2, drawn randomly from the state transition distributions, and so on. Okay, so switch back to this board on the left. So after your robot does this for a while, it will have visited some sequence of states, S0, S1, S2, and so on. And to evaluate how well we did, we'll take the reward function and we'll apply it to this sequence of states and add up the sum of rewards that your robot obtained on the sequence of states it visited, right? So you're in state S0, you take an action, you get to S1, take an action, you get to S2, and so on. So take the reward function and apply it to every state in the sequence, and this is the sum of rewards you obtain. I'm going to change this formula just one more bit. I'm going to multiply this by gamma squared, and the next term will be multiplied by gamma cubed, and so on. Okay, and this is called, and I'm going to call this the total payoff for the sequence of states S0, S1, S2, and so on that your robot visited. And so let me now say what gamma is, right? So you recall that gamma is a number that's strictly less than 1. So usually you think of gamma as a number like 0.99. So the effect of gamma is that the reward you obtain at time 1 is given a slightly smaller weight than the reward you get at time 0. And then the reward you get at time 2 is even a little bit smaller than the reward you get at a previous time step, and so on. Let's see. And so if this is an economic application, if you like build a stock market trading reinforcement learning algorithm or whatever, if this is an economic application, then and if your rewards are dollars earned and lost, then the discount factor gamma has a very natural interpretation as the time value of money, right? Because like $1 today is worth slightly less than $1 today is worth slightly more than $1 tomorrow, because if I put the dollar in the bank, I can earn a little bit of interest. And conversely, having to pay out $1 tomorrow is better than having to pay out $1 today. So in other words, the effect of the discount factor gamma is that it tends to weight wins or losses in the future less than wins or losses in the immediate future. It tends to weight wins and losses in the distant future less than wins and losses in the near term. Okay. And so the goal of the reinforcement learning algorithm is to choose actions over time. So to choose actions A0, A1, and so on, to try to maximize the expected value of this total payoff. Okay. And more concretely, what we will try to do is have our reinforcement learning algorithms compute a policy which are denoted by the lowercase pi, which and all a policy is, the definition of a policy is a function mapping from the states to the actions. And so it goes to come with a policy that tells us, so for every state, what action it recommends we take in that state. So concretely, here is an example of a policy. Well, and this actually turns out to be the optimal policy for the MDP. And I'll tell you later how I computed this. Okay, and so this is an example of a policy. The policy is just a mapping from states to the actions, And so a policy tells me, when you're in this state, you should take the left action. And this particular policy that I drew out happens to be the optimal policy in the sense that when you execute this policy, this will maximize your expected value of the total payoff. This will maximize your expected total sum of discounted rewards. Yeah?
Can a policy be over multiple states?
Yeah, so can a policy be over multiple states? So can it be over as a can it be a function of not my current state, but the state that was in previously as well? So the answer is yes. Sometimes people call them strategies instead of policies, but usually you can also call them policies. It actually turns out that for an MDP, allowing policies that depend on my previous states will not allow you to do any better, at least in the limited context we're talking about. So in other words, there exists a policy that only ever looks at the current state and will maximize my expected total payoff. And this statement won't be true for some of the richer models we talk about later, but for now, all we need to do is, it suffices just look at the current state and choose an action. And sometimes I use the term execute a policy to mean that I'm going to take actions according to a policy. So I say I'm going to execute the policy pi. That means that I'm going to, whenever I'm in some state S, I'm going to take the action that the policy pi, outputs when given the current state. All right. So it turns out one of the things that MDPs are very good at is right, let's look at that state. Say the optimal policy in this state is to go left. Is actually, this probably wasn't very obvious. Why is it that the optimal action is to go left and take the longer path there, right? The alternative would be to go north and try to find a much shorter path to the +1 state. But when you're in this state over here, right, this I guess 3,2 state, when in that state over there, when you go north, there's a 0.1 chance you accidentally veer off to the right to the -1 state. And so there are these subtle trade-offs. Is it better to take the longer and safer route? But the discount factor would tend to discourage that, and the 0.02 charge per step would tend to discourage that. Or is it better to take a shorter but riskier route? And so probably it sort of wasn't obvious to me until I computed it that this is the optimal action. And this is one of the things that MDP machinery is very good at making, to make subtle trade-offs like these optimally. So what I want to do next is make a few more definitions, and that will lead us to our first algorithm for computing optimal policies in MDPs, so finding optimal ways to act in MDPs. Before I move on, let me just check any questions about the MDP formalism before. Okay, cool. So let's now talk about how we actually go about computing an optimal policy like that. And to get there, I need to define a few things. So, well, just as a preview of the next few steps I'm going to take, I'm going to define something called V pi, and then I'm going to define V star, and then I'm going to define pi star. And it will be a consequence of my definitions that pi star is the optimal policy. Okay, and so you can say, as I define these things, just keep in mind what is a definition and what is a consequence of the definitions. In particular, I won't be defining pi star to be the optimal policy, but I'll define pi star via a different equation, and it'll be a consequence of my definition that pi star is the optimal policy. So first thing I want to define is V pi. So for any given policy pi, I'm going to define the value function V pi, and sometimes I call this the value function for pi. So I'm going to define the value function V pi as a function mapping from the states to the real numbers, such that V pi of S is the expected payoff is the expected total payoff, right? If you start in the state S, and if you execute pi. Okay, so in other words, V pi of s is equal to the expected value of this, sum of discounted rewards, the total payoff, given that you execute the policy pi and the first state in the sequence S0 is that state S. I say this is slightly sloppy probabilistic notation, so pi isn't really a random variable, so really I shouldn't actually be conditioning on pi, but this is sort of moderately standard notation in RL, so I'm going to use the slightly sloppy probabilistic notation. So as a concrete example, as a concrete example, here's a policy, right? Okay, and this is not a great policy. This is just some policy pi. It's actually a pretty bad policy that for many states seems to be heading to the -1 rather than +1. And so the value function is a function mapping from the states to the row numbers. So it associates each state with a number. And in this case, this is V pi. So this is 0.52. And so that's the value function for this policy. And so you notice, for instance, that for all the states in the bottom two rows, I guess this is a really bad policy that has a high chance of taking you to the -1 state. And so all the values for the all the values for the states in the bottom two rows are negative. Since on expectation your total payoff will be negative if you execute this rather bad policy and you start in any of the states in the bottom row. And if you start in the top row, then the total payoff will be positive. This is not a terribly bad policy for the states in the topmost row. Okay. And so given any policy, you can write down a value function for that policy. So some of you are still writing. Let's leave that up for a sec while I clean another couple of boards. Right. Okay. So let's consider the following. V pi of s is equal to, right, the expected value of R of S0, which is the reward you get, right away for just being in the initial state S, plus, and I'm going to write this like this. I'm going to write gamma, and then R of S1 plus gamma R of S2 plus dot dot dot. Condition on pi. Okay, so just re-parenthesize these. This first term here, this is sometimes called the immediate reward. This is the reward you get right away just for starting in the state S0. And then the second term here, these are sometimes called the future rewards, which are the rewards you get, sort of one-time step and further into the future. And I want you to notice what this term is, right? That term there is really just the value function for the state S1, because this term here in parentheses, this is really, suppose I were to start in the state S1, what is the sum of discounted rewards I would get if I were to start in the state S1, right? So my immediate reward starting from state S1 would be R of S1, and then plus gamma times additional future rewards into the future. And so it turns out you can write V of pi recursively in terms of itself. And in particular, V of pi is equal to the immediate reward plus gamma times, and actually, let me just remap this notation. Right? So S0 gets mapped to S, and S1 gets mapped to S prime in this next line, right? So value function for pi applied to state 0 is the immediate reward plus discount factor gamma times, and now it needs to have V pi of S1, which I'm writing as V pi of S prime. But S prime is a random variable, because the next state you get to after one-time step is random. And so in particular, so if taking expectations, this is a sum of all states S prime of your probability of getting to that state times that, okay? And just to be clear on this notation, right, this is P subscript SA of S prime is the chance of you getting to the state S prime when you take the action A in state S. And in this case, we're executing the policy pi. And so this is P of S pi of S because the action we're going to take in state S is the action pi of S. So this is so in other words, this PS pi of S, this is the distribution over states S prime that we will transition to in one-time step when we take the action pi of S in the state S. Okay. So just to give this name, this equation is called Bellman's equations, and is sort of one of the central equations that we'll use over and over when we solve MDPs. You're still writing. Could you just raise your hand if this equation makes sense? Some of you didn't raise your hands. Do you have questions? So let's try to say this again. Actually, which of the symbols don't make sense for those of you that didn't raise your hands? You're regretting not raising your hand now, right? Let's try to say this one more time, and maybe it'll become clearer later. What is it? So this equation is sort of, right, my value at the current state is equal to R of S plus gamma times, and then depending on what state I get to next, my expected total payoff from the state S prime is V pi of S prime, right? Where S prime is the state I get to after one-time step. So I'm currently in state S, I'm going to take some action and I get to some state S prime, and this equation is sort of my expected total payoff for executing the policy pi from the state S. But S prime is random because the next state I get to is random. Well, let me use the next word. The chance I'll get to some specific state S prime is given by, P subscript SA S prime, where, because these are just my state transition probabilities, where the action A I chose is given by pi of S because I'm executing the action A in the current state S. And so when you plug this back in, you get P subscript S pi of S S prime just gives me the distribution over the states I'm likely to transition to in one step. And hence, that gives me Bellman's equations. So it turns out that Bellman's equations gives you a way to solve for the value function for a policy in closed form. So again, the problem is, suppose I'm given a fixed policy. How do I solve for V pi? How do I solve for the So given fixed policy, how do I solve for this equation? It turns out Bellman's equations gives you a way of doing this. So coming back to this board, it turns out to be, just want to come back to the previous board, could you move the camera to point to this board? Okay, cool. So going back to this board, if you look at Bellman's equations, which is this equation, let's say I have a fixed policy pi and I want to solve the value function for the policy pi. Then what this equation is, this imposes a set of linear constraints on the value function, right? So in particular, this says that the value for a given state is equal to, some constant plus, and then some linear function of other values. And so you can write down one such equation for every state in your MDP, and this imposes a set of linear constraints on what the value function could be. And then it turns out that by solving the resulting linear system of equations, you can then solve for the value function v pi of s. Okay, that was a high-level description. Let me now make this concrete. So specifically, let me take the free one state, that state we're using as an example. So Bellman's equations tells me that the value for pi for the free one state, and let's say I have a specific policy so that pi of free one, let's say it takes a north action, right, which is not the optimal action. But for this policy, Bellman's equation tells me that v pi of free one is equal to r of the state free one, and then plus gamma times, with chance 0.8, I'll get to the free 2 state. With chance 0.1, I'll get to the, what's this? Full 1 state. And with chance 0.1, I will get to the 2-1 state. And so what I've done is I've written down Bellman's equations for the free one state. I hope you know what I mean. So, right, so in my little MDP, right, I'm indexing the states 1, 2, 3, 4, 1, 2, 3. So this state over there, right, where I drew the circle, is the free one state. So for every one of my 11 states in the MDP, I can write down an equation like this. Just done just for one state. And you notice that if I'm trying to solve for the values, so if these are the unknowns, then I will have 11 variables because I'm trying to solve for the value function for each of my 11 states. And I will have 11 constraints because I can write down 11 equations of this form, one such equation for each one of my states. So if you do this, if you write down this sort of equation for every one of your states in your MDPs, you have a set of linear equations with 11 unknowns and 11 variables. 11 constraints or 11 equations with 11 unknowns. And so you can solve that linear system of equations to get an explicit solution for v pi. Okay, because you have, if you have n states, you end up with n equations and n unknowns. You can solve that to get the values for all of your states. Okay, cool. So, actually, could you please raise your hand if this made sense? Just cool. All right, so that was the value function for a specific policy and how to solve for it. Let me define one more thing now. So the optimal value function, I'm defined as v star of s equals taking a max over all policies pi of v pi of s. So in other words, for any given state s, the optimal value function says, suppose I take a max over all possible policies pi, what is the best possible expected sum of discounted rewards that I can expect to get? What is my optimal expected total payoff for starting a state S instead of taking a max over all possible control policies pi. So it turns out that there's a version of Bellman's equations for V star as well. So this is also called Bellman's equations for V star rather than for V pi. Now just write that down. So this says that the optimal payoff you can get from a state S is equal to, so I'll fill in some more things here, right? So let's see, just for starting off in the state S, you're going to get, you're going to get your immediate reward R of S. And then depending on what action A you take, right, your expected total payoff will be given by this. Right, so if I take an action A in some state S, then with probability given by P subscript SA of S prime, right, by this probability I transition to state S prime. And when I get to the state S prime, I'll expect my total payoff from there to be given by V star of S prime, because I'm sort of now starting a new state S prime. So the only bit in this equation I need to fill in is what is the action A. So in order to actually obtain the optimal expected payoff, and to actually obtain the maximum or the optimal expected total payoff, what you should choose here is the max overall actions A. Is choose your action A that maximizes the expected value of your total payouts as well. Okay, so this makes sense. This is a version of Bellman's equations for V star rather than V pi. And just say it again. It says that my optimal expected total payoff is my immediate reward plus, and then the best action I can choose, the max overall actions A of my expected future payoff. Okay, and this also leads me to my definition of pi star, right? Which is, let's say I'm in some state S and I want to know what action to choose. Well, if I'm in some state S, I'm going to get an immediate reward R of S anyway. So what's the best action for me to choose is whatever action will enable me to maximize the second term. As well, if my robot is in some state S and I want to know what action to choose, I want to choose the action that'll maximize my expected total payoff. And so pi star of S is going to define as argmax over actions A of of this same thing. Okay, and I could also put the gamma there, but gamma is just a positive. Well, gamma is almost always positive, so I'll just drop that. So since it's just a constant scaling factor and doesn't affect the argmax. And so a consequence of this definition is that pi star is actually the optimal policy, right? Because pi star will maximize my expected total payoffs. Cool. Any questions at this point? Cool. So what I'd like to do now is talk about an algorithm to actually compute pi star, to compute the optimal policy. I should write down a little bit more before I do that. But notice that if I can compute V star, right, if I can compute the optimal value function, then I can plug it into this equation and then I'd be done, right? So if I can compute V star, then using this definition for pi star, I can compute the optimal policy. So my strategy for computing the optimal policy will be to compute V star and then plug it into this equation, and that will give me the optimal policy pi star. So my goal, my next goal will really be to compute V star. But the definition of V star here doesn't lead to a nice algorithm for computing it, because let's see. So I know how to compute V pi for any given policy pi by solving that linear system of equations. But there's an exponentially large number of policies, right? So I guess if you have 11 states and 4 actions, then the number of policies is 4 to the power of 11. This is sort of a huge space of possible policies, and so I can't actually exhaustively enumerate all policies and then take a mass to compute V star. So I should write down some other things first, just to ground the notation. But what I'll do is eventually come up with an algorithm for computing V star, the optimal value function, and then we'll plug it into this, and that will give us the optimal policy pi star. And so let me I'll write down the algorithm in a second, but just to ground the notation. Well, yeah, no, let's skip that. Okay, let's just talk about the algorithm. So this is an algorithm called value iteration, and it makes use of Bellman's equations for the optimal policy to compute V star. So here's the algorithm. Okay, and that's the entirety of the algorithm. So, and you repeat this step, I guess. You repeatedly do this step. So just to be concrete, let's say in my MDP of 11 states, the first step is initialize V of S equals 0. So what that means is I'll create an array in my computer implementation. Create an array of 11 elements and say set all of them to 0. It turns out you can initialize them to anything. It doesn't really matter. And then what we'll do is we'll take Bellman's equations and we'll keep on, taking the right-hand side of Bellman's equations and overwriting and sort of copying down on the left-hand side. So we'll essentially iteratively try to make Bellman's equations hold true for the numbers V of S that we're storing away. Okay, so V of S here is an array of 11 elements, and I'm going to repeatedly, compute the right-hand side and copy that onto V of S. And it turns out that when you do this, this will make V of S converge to V star of S. So maybe no surprise, because we know V star of S must satisfy Bellman's equations. You get to play with some of these ideas a bit more in the problem set, so I won't prove the convergence of this algorithm. Some implementational details. Turns out there are two ways you can do this update. One is when I say for every state S perform this update, one way you can do this is for every state S, you can compute the right-hand side, and then you can simultaneously overwrite the left-hand side for every state S. And so if you do that, that's called a synchronous update. Right, and synchronous is if you sort of update all the states S simultaneously. And if you do that, it's sometimes written as follows. If you do a synchronous update, then it's as if you have some value function, at the ith iteration or the tth iteration of the algorithm, and then you're going to compute some function of your entire value function, and then you're going to set your value function to this new version. We sort of simultaneously update all 11 values in your estimated value function. So it's sometimes written like this, where B here is called the Bellman backup operator. So in the synchronous value iteration, you sort of take the value function, you apply the Bellman backup operator to it, and the Bellman backup operator just means computing the right-hand side of this for all the states, and then you overwrite the entire value function. The other way of performing these updates is asynchronous updates, which is where you update the states one at a time. So I would, go through the states in some fixed order. Say I would update V of S for state number 1, and then I would update V of S for state number 2, then state number 3, and so on. And when I'm updating V of S for say state number 5, if V of S prime, if I end up using the values for states 1, 2, 3, and 4 on the right-hand side, then I'd use my recently updated values from the right-hand side. Okay, so if you update the thing sequentially, so that we're updating the 5th state, you'd be using the values or the new values for states 1, 2, 3, and 4. And that's called an asynchronous update. And both versions will cause V of S to converge to V star of S, so you can implement asynchronous updates are maybe just like a tiny little bit faster, but both work fine. And it turns out in the analysis of value iteration, synchronous updates are also easier to analyze. And so just in practice, both work about equally well. Asynchronous being just a little bit faster. Okay. So, when you run this algorithm on the MDP, oh, I forgot to say, all these values were computed with gamma equals 0.99. And actually, Roger Gross, who's a I guess master student here at Stanford, helped me with computing some of these numbers. So when you compute when you run value iteration on this MDP, the numbers you get for V star are as follows: 0.86, 0.90. And again, you know, the numbers sort of don't matter that much, but just take a look at it and make sure it sort of intuitively makes sense. So, and then when you plug this into the formula for computing that I wrote down earlier, for computing pi star as a function of V star, then, well, I drew this previously, but here's the optimal policy pi star. Okay, and so just to summarize, the process is I run value iteration to compute V star. So this gives me this table of numbers, and then I use my formula for pi star to compute the optimal policy, which is this policy in this case. And again, just to be completely concrete, right? Let's look at that free one state again. Is it better to go left or is it better to go north? So let me just illustrate why I'd rather go left than north, right? So in the formula for pi star, if I go west, then sum over S prime PSA S prime P star of S prime. This would be well, let me just write this down. Right. Whereas if I go north, then will be equal to that. I wrote that down really quickly, so some of you are still writing. So the way I got these numbers is, suppose I'm in this state, suppose I'm in this free one state. If I choose to go west, then with chance 0.8, I get to 0.75, to this state with 0.75. With chance 0.1, I veer off and get to the 0.69, and with chance 0.1, I go south and I bounce off the wall and I stay where I am. So that's why my expected future payoff for going west is 0.8 times 0.75 plus 0.1 times 0.69 plus 0.1 times 0.71. So the last 0.71 being if I bounce off the wall to the south and end up staying where I am, that gives me 0.740. You can then repeat the same process to estimate your expected total payoff if you go north. So if you do that, with 0.8 chance, you end up going north, so you get 0.69. With 0.1 chance, you end up here, and 0.1 chance, you end up there. Just map these mentally to that expression, and compute that expectation, you get 0.676. And so your total payoff is higher if you go west. Your expected total payoff is higher if you go west than if you go north. And that's why the optimal action in this state is to go west. Okay. So that was value iteration. It turns out there are two sort of standard algorithms of computing optimal policies in MDPs. Value iteration is one, which is some of you still writing. So value iteration is one, and the other, so standard algorithm for computing optimal policies in MDPs is called policy iteration. And let me just go and write this down. So in policy iteration, we initialize the policy pi randomly. So it doesn't matter. It can be the policy that always goes north. It can be a policy that takes actions at random, whatever. And then we'll repeatedly do the following. Okay, so that's the algorithm. So the algorithm has two steps. In the first step, we take the current policy pi, and we solve Bellman's equations to obtain V pi. So remember, right, earlier I said that if you have a fixed policy pi, then Bellman's equations defines this system of linear equations with 11 unknowns and 11 linear constraints. And so you solve that linear system of equations to get the value function for your current policy pi. And by this notation, I mean just let V be the value function for the policy pi. Then the second step is you update the policy, in which you pretend that your current guess V for the value function is indeed the optimal value function, and you let pi of s be equal to that argmax formula to update your policy pi. And so it turns out that if you do this, then V will converge to V star, and pi will converge to pi star. So this is another way to find the optimal policy for an MDP. In terms of trade-offs, so it turns out that, let's see, in policy iteration, the computationally expensive step is this one, right, where you need to solve this linear system of equations, with n equations and n unknowns if you have n states. And so if you have a problem with a relatively few number of states, if you have a problem with like 11 states, you can solve a linear system of equations fairly efficiently. And so policy iteration tends to work extremely well for problems with smallish numbers of states where you can actually solve this linear system of equations efficiently. So if you have like 1,000 states or anything less than that, you can solve the system of 1,000 equations very efficiently. So policy iteration will often work fine. If you have an MDP with enormous number of states, so we'll actually often see MDPs with tens of thousands or hundreds of thousands or even millions or tens of millions of states. If you have a problem with 10 million states and you try to apply policy iteration, then this step requires solving a linear system of whatever 10 million equations, and this would be computationally expensive. And so for these really, really large MDPs, I tend to use value iteration. Okay. Let's see. Cool. Any questions about this?
So this is the convex function because this is a local optimization scheme, right? I mean.
Yeah. Yes, you're right. It's a great question. So this is a convex function. It actually turns out that there is a way to pose the problem of solving for V star as a convex optimization problem, as a linear program. So it turns out you can write down, solution. You can write down V star as a solution to a linear programming problem you can solve. Policy iteration converges, is guaranteed to converge and will not get stuck in local optima, but the proof of the convergence of policy iteration sort of uses somewhat different principles in convex optimization. At least the versions of proof that I could see. Yeah, you could probably relate this back to convex optimization, but not in the standard proofs of why this algorithm converges. Yeah, the proof is not that difficult, but it's also sort of longer than I want to go over in this class. Yeah, this is a good point. Cool. Actually, any questions about any of this? Okay. So we now have two algorithms for solving MDPs, right? So given the 5-tuple, given the set of states, the set of actions, the state transition probabilities, the discount factor, and the reward function, you can now apply policy iteration or value iteration to compute the optimal policy for an MDP. The last thing I want to talk about is what if you don't know the state transition probabilities. And sometimes you won't know the reward function R as well, but let's leave that aside, right? And so, so for example, let's say you're trying to fly a helicopter and you don't really know in advance what state your helicopter will transition to when you take an action in a certain state, because helicopter dynamics are kind of noisy. You sort of often don't really know what state you end up in. So the standard thing to do, or one standard thing to do, is then to try to estimate the state transition probabilities from data. Okay. Oh, and let me just write this out. So it turns out that, right, the MDP has this 5-tuple, right? SA, you know, the transition probabilities, gamma, and R. S and A, you almost always know. The state space is sort of up to you to define, right? What's the state space of your robot, or the factor you're trying to control, whatever. Actions is, again, just what are your actions. Usually, you almost always know these. Gamma, the discount factor, is something you choose depending on, you know, how much you want to trade off current versus future rewards. The reward function you usually know. There are some exceptional cases. Usually, you come up with a reward function, and so you usually know what the reward function is. Sometimes you don't, but let me just leave that aside for now. And the most common thing for you to have to learn are the state transition probabilities. So let me just talk about how to learn that. So well, if you don't know state transition probabilities, the most common thing to do is to just estimate it from data. So what I mean is, you imagine you have some robot, maybe it's a robot wandering around the hallway, like in that grid example. You would then have the robot, you know, just take actions in the MDP, and and you would then estimate your state transition probabilities P subscript SA of S prime to be, you know, so pretty much exactly what you'd expect it to be. This would be the number of times you took action A in state S and you got to S prime, divided by the number of times, right, you took action A in state S. Okay, so estimate this as just, of all the times you took the action A in state S, what's the fraction of times you actually got to the state S prime? So it's pretty much exactly what you would expect it to be. Or you can, or in case you've never actually tried action A in state S, so if this turns out to be 0 over 0, you can then have some default estimate for this, like a uniform distribution over all states. So this is reasonable default. And so, putting it all together, and by the way, it turns out in reinforcement learning, so in most of the early parts of this class, right, in supervised learning, you know, I sort of talked about the logistic regression algorithm and the DESI algorithm, and most implementations of logistic regression, you know, so it's like a fairly standard way to do logistic regression or SVMs or factor analysis or whatever. It turns out in reinforcement learning, you know, there's more of a mix and match sense, I guess. There are often different pieces of different algorithms you can choose to use. So in some of the algorithms I write down, there's sort of more than one way to do it, and I'm sort of giving specific examples. But if you're faced with an RL problem, something you want to control a robot, you know, you want to plug in value iteration here instead of policy iteration. You want to do something slightly different than one of the specific things I wrote down. That's actually fairly common. So just in reinforcement learning, there's sort of a broader range of ways to apply different algorithms and mix and match different algorithms. And this will come up again in the next few lectures. But so just putting the things I said together, here would be a, you know, this would be an example of how you might estimate the state transition probabilities in an MDP and find a policy for it, right? So you might repeatedly do the following. Let's see. Right, take actions using some policy pi to get experience in the MDP, meaning that you just execute the policy pi observe state transitions. Based on the data you get, you then update estimates of your state transition probabilities P subscript SA, based on the experience of the observations you just got. Then you might solve Bellman's equations using value iteration, say, which I'm abbreviating to VI. And by Bellman's equations, I mean Bellman's equations for V star, not for V prime. And solve Bellman's equations using value iteration, to get an estimate for V star. And then you update your policy pi of S equals argmax and now you have a new policy, so you can then come back and execute this policy for a bit more in the NDP to get some more observations of state transitions, get more experience in NDP, use that to update your estimates of the state transition probabilities again, use value iteration or policy iteration to solve for a new estimate of the value function, get a new policy, and so on. Okay, and it turns out when you do this, I actually wrote down value iteration for a reason. It turns out that in this third step of the algorithm, if you're using value iteration rather than policy iteration, to initialize value iteration, if you use your solution from the previous loop through this algorithm, right, then that's a very good initialization condition, and this will tend to converge much more quickly. Just value iteration tries to solve for V of S for every state S, right? Or it tries to estimate V star of S, and the estimate is stored in V of S. And so if you're looping through this, and if you initialize your value iteration algorithm using the values you had from the previous round through this, then that will often make this converge faster. But again, this is you can also just as well plug in policy iteration in here as well, whatever. And this is a fairly typical example of how you would solve a policy, collect data in NP, and try to find a good policy for a problem for which you did not know the state transition probabilities in advance. Cool. Questions about this? Cool. So, aren't you guys excited? This is like, our first 2 MDP algorithms in just one lecture. All right, let's close for today. Thanks.